All right, thank you everybody for coming today. Thank you especially given that this is the very final session of the event. So I really appreciate you staying on. My name's Ben Allison. I'm a machine learning scientist with Amazon. I work at the development center in Edinburgh. And over the next 50 minutes or so, my plan is to talk to you about some work that we've done out of Edinburgh in collaboration with the Personalization organization in Seattle as part of Amazon's recommendations program. And it's some work where we really wanted to take a step back and think about what recent advances in machine learning, kind of core machine learning and its closely related applied disciplines, had to say about the problems of recommendations and understanding customers and their preferences and things like that. There is a certain amount of technical material in the talk. It's quite a technical subject, but I've tried to keep it relatively high level. For those of you that do want the technical details, there's a paper that hopefully will be coming out in the next few days. So I promise I will keep it as high level as I possibly can whilst trying to give you some of the ideas. The other thing I want to say, and it's maybe more of an apology or an ask for forgiveness, is a lot of the stuff that you've heard over the course of this event has been quite actionable. It's been like a call to action, use this thing that AWS provides. This is more of a talk about specific ways that we can solve problems at Amazon if you're willing to go beyond the kind of commodity solutions that AWS provides to a more bespoke solution. And hopefully for reasons that will become clearer during the course of the talk, it would be hard to make this a commodity service. But hopefully the insights and the ideas will still be interesting and applicable to you. So what I'm going to do is I'm going to take you on a tour of how you can think about the recommendations problem through to the system that we built that is now, it's certainly not serving all recommendations at Amazon, but it's serving an increasing number of recommendations across diverse contexts on the Amazon website across the world. So I'm not a big fan of agenda slides, but this is my agenda. I'll try to motivate the recommendations problem. Exactly why you might want to do recommendations, I probably don't need to convince you of, but I'll try and give you a perspective on recommendations at least that might be useful. I'll talk about how we can think about recommendations as a learning problem. That's going to be quite an important insight for the later material. I'll then say something about why I think we might want to think about applying deep learning techniques to the problem of recommendations. And then the last bit I'll get to is the nature of the recommendations problem and the paradigm that we want to approach it from. I should say, most of the sessions that I've been to this week have been quite lecture style. I talk, you listen. I'm used to doing things more interactive, so if you do want to interrupt and ask questions, go ahead, or else you can ask questions at the end. Okay, so why do we care about recommendations? I'm going to make a gross generalization and say that when a customer comes to an online store, or maybe even a physical store, there are two very broad kinds of customers or customer missions that might exist. One is a customer that does something that we often at Amazon call spear phishing, right? So the customer comes in with a particular product or maybe a class of products in mind, and what we want to do is give them that product with the best possible convenience, at the lowest possible price, with the best possible shipping. Right? Recommendations doesn't have very much to say about that experience. It's a problem of search and navigation and then logistics and optimization. Where recommendations really comes in is the other kind of customer who comes to the store maybe to browse or as a leisure activity or just to be inspired by something, right? And recommendations is part of the solution to the problem of discovery, right? And so Amazon as a retailer has an enormous catalog of products, hundreds of millions of items that you can buy, and there is no hope for a customer to browse through that selection of products, and so what we have to do is provide you with tools and experiences that help with the discovery there. And that's where I think recommendations fits in, and that's the context that I want to situate this work in. So what can you do to aid discovery in a physical store? Well, your levers, your options are fairly limited, right? So imagine you want to optimize the shopping experience for discovery in a physical store. Basically, all you can do is control store layout and placement of products on shelves, right? And in addition to that, you can everybody receives the same experience, right? So maybe you're really smart and you've heard about this idea of using analytics, and so you look at data about your customers' shopping patterns in order to try and optimize the layout of the store to aid discovery. But everybody has the same experience. Your levers are fairly limited. So all you can do is optimize for the average customer, right? In the world of online retailing, you have much more sophisticated levers. So this is a shot of the Amazon desktop gateway, I think, from my account from a month or so ago. And what you can see here is that there's a bunch of, okay, the pointer doesn't work. There's a bunch of content across the top that's specifically related to me. So it says, "Hi, Ben," and it has some information about orders that I've made recently and movies I might have watched and things based on my Audible history and stuff like that. Content that's customized to me, the individual, and somebody else would see something different. And so what I could decide to do for a different customer, or if I knew something different about my own particular preferences, is I could say, well, I want the experience to be completely different. Maybe I want to delete the thing about my first order, and I want to move the deal of the day into a more prominent location because I'm more interested in deals or something like that. So what I'm trying to get across here is that the world of online retailers gives you much more sophisticated affordances for customizing the shopping experience. And then the real core of recommendations is what you see when you get a little bit further down the page. And what I'm going to talk about for the rest of this talk is a system, an algorithm, an idea that powers content a bit like you can see with these rows here, right? So this is recommendations for you in books. How do you go about generating those rows of content when there are tens of millions of possible things that you could put there, and in this case, I've got 9 things on the screen. How do I go about even choosing those things? And how can I make it so that they're the most relevant and most interesting for me, the individual? So what I try to do is say something about the promise of recommendations in an online context, which is I've got all these really sophisticated affordances so that the experience can be uniquely customized to you, the individual. But the reality is, with the complexity of the levers that the online experience affords, there are some downsides as well. So the scale is very large, right? A typical physical retailer might have to deal with tens of thousands of product lines and maybe millions of customers over the course of the year if they were very big. Whereas at Amazon, we have to deal with tens, hundreds of millions of products and hundreds of millions of customers. So by definition, the problem is that much harder because the scale is orders of magnitude larger. Also, the online world especially, I mean, shopping trends move quite quickly anyway, but in the online world, they move even more quickly, right? So you want those affordances to be timely in a world that's changing very quickly. And the idea of using data driven from our customers to optimize the experience is nice, but the reality is, we only have a very narrow and constrained insight into what you do that comes through the implicit behaviors that you make when you're interacting with Amazon. And so inferences that we might draw can be quite hard because they can be quite noisy, right? We don't know a lot of things about you that would make it easier to figure out what to do. So what do we want to do? We want to build a recommendation system that speaks to this idea of discovery, that helps you find products that you're going to love. And a phrase that we often use at Amazon to describe the idea of what we're looking to drive is serendipity, right? So what we want to do is help you find products that you didn't know existed, but when we tell you about them, you'll love them, right? That's exactly the use case that we're trying to help. And we also want the recommendations systems that we build to help you navigate this very large space of products that you could never hope to do on your own. So we're also trying to make the browsing experience much more friendly for you. And ultimately, what we want to do is build a data-driven and objective optimization of the shopping experience that's customized to you, the individual. And that's what, in my mind at least, the ideal recommendation system should be doing. Okay, so how are we going to go about doing that? I'm going to try and make the case for why you want to think of recommendations as a learning problem. right? So how do we drive towards those outcomes that I was describing using ideas from machine learning? So the main reason why I think you want to think of this as a learning problem is because otherwise you're going to end up trying to write down heuristics for what you want to happen, right? So either you can use data to try and inform the right thing to do, or you can say, I, the individual, think that customers should get this kind of shopping experience. But my ideas, or any individual's ideas, or even teams of people, are not going to cover all of the possible use cases. They're going to be subject to the biases or the likes that we have as individuals. And so it would be better if we just reflected the preferences of our customers directly through the data. And we've got quite a lot of it, right? Maybe you've been sold on the promise of data and the insights that you can drive from it. Amazon is in a unique position of having quite a lot of information about our customers and their preferences. So we'd like to use that data to help drive the best possible experience that we can for our customers. And the third reason why I think we want to think of it as a learning problem is just this idea of taking a specific problem, understanding the abstractions that underlie it, and then being able to leverage a much broader and richer suite of tools from a range of disciplines. And I think that's the promise of thinking of recommendations as a pure learning problem. So I want to give you a little bit of context into how recommender systems used to be built. So early approaches would use the name collaborative filtering, right? And there are two broad strands of collaborative filtering. There is something called user-based collaborative filtering and item-based collaborative filtering. So they're kind of similar, but mirrored around each other. So a user-based collaborative filtering system will say, in order to make recommendations to you, the individual, I want to find customers that are similar to you, and I want to recommend products that they bought that you haven't bought. And item-based collaborative filtering says, I want to find the things that you, the individual, have bought. I want to find products that are similar to those, and I want to recommend you those if you've not bought them already. So these sort of fell out of favor, and I think some of it is just broader trends in the literature, but one of the main reasons why they fell out of favor is this notion of similarity between customers, similarity between products, is a difficult one to define, and it's an even harder one to optimize, right? I'm back in the realm of saying, well, this is what I think it means for two customers to be similar, but how do I know that my definition of similarity is the right definition? And because I don't have an objective measure of performance, it's quite hard to iterate and make improvements to the algorithm. So that's why we've switched to more pure learning approaches. So what I want to do now is introduce the idea of how you can use learning to drive a recommendations engine. And so I've got a cartoon sketch of a recommender whose entire behavior is controlled by a single parameter, W, on the x-axis. And I've got this idea of a loss function on the y-axis. So the first thing to note is that for somewhat arbitrary reasons in machine learning, we talk about loss functions where lower is better, rather than almost everywhere else in the world where higher is better. So what we want to do is figure out how to get the setting of the parameter that gets to the bottom of this slope, not the top. So I want you to imagine in your mind that my recommender system's behavior could be entirely described by a single parameter W, okay? It's a bit of a stretch, but it's easier to do it in one dimension than hundreds of millions. So the idea is, for some setting of W, I can figure out what the value of the loss function is at that setting. And the loss function is just my idea of how good the recommender is if I set W to that value. So it's some measure of performance or goodness of the recommender, right? And then basically what I do is I follow this algorithm, this procedure, where I guess at what W might be. I evaluate the loss function. I figure out, using some calculus, the direction in which the loss is getting lower, and I step a bit in that direction, and I iterate. And I keep going until the function is not getting any smaller, no matter which direction I move in, or I get bored and stop. And that's the setting of W that I want to use for my recommender. So this is a relatively simple idea in one dimension, and what I did was I described gradient descent for those of you that are familiar with it. Gradient descent on a loss function that I haven't really spoken about yet, but we'll get to that later on. But this idea of a loss function is crucial because what I've done is I've wrapped up the idea of how good my recommender system is in this smooth function J, the loss function, and now I can just use standard mechanisms to find the best possible setting of the parameters that control my recommender system. And that's a very powerful idea. So I showed you a picture in one dimension. The reality is the kind of models that we're optimizing have 200 million dimensions instead, but hopefully, and there's something called non-convex as well, which means that they don't have a single nice dip at the bottom. They have dips and bumps and valleys everywhere, but the broad ideas basically work there as well. Okay, so hopefully I've convinced you that thinking of recommendations as a learning problem is a good idea. And now we have to figure out how to take the data, the sort of abstract definition of the problem, and turn it into something that we can learn about. And in order to do that, some of you that are familiar with machine learning might know we need to come up with features of the problem so that we can plug them into learning algorithms. So in the context of recommendations, the things that I need features about are products and customers, right? I want to say how well some customers are going to like other products. So here's a shot of the detail page of the Nintendo Switch from a little while ago. And what I want to do to figure out how well certain customers might like this product is turn that into a feature vector. Okay? Feature vector is just a vector of numbers that describes different aspects of the product. So the easiest way to do it, the way that almost everybody does when they're getting started, is to do it by hand, right? So I, the human who understands the domain well, sit down and figure out what aspects of this product are going to be important to describe which users like it and which don't. So in the context of a games console, or indeed a product on Amazon, that might be things like, what's the brand of the product? What's the average review score of the product? What's the price? Can I extract some features from the description of the product that talk about games consoles and things like that? Maybe I want to pay attention to stock levels or the fact that it's an Amazon Choice product, all those kinds of things, right? And so what I can do is, as somebody with lots of domain expertise, I can laboriously write down all of the bits of information about this product that will lead me to be able to explain user interactions with it. And that has some upsides. It's pretty easy to get started. It's pretty easy to take my domain expertise and apply it to build a system that sort of works. It's easy to make it better. I can iterate quickly because when I have a new idea for what to do, I just encode it as a feature, and if it explains the data better, great. And the other thing is, if it doesn't work very well, then I have a very interpretable model so that I can introspect it and say, what's going on here? Why is this not working the way I think it is? That's great. But that's typically not the way that we solve recommendations problems, and I'm going to try and convince you why. So the alternative is to think of the feature vector for the Nintendo Switch as some extra parameters in the model that are going to be learned, right? So in the setting that I was talking about before, where I was showing the optimization problem, there was one dimension. Now imagine the Nintendo Switch product on its own has 50 dimensions that relate specifically to that product. I can try and set those numbers as free parameters in the model, along with the things that regulate behavior of the model with respect to those features, right? I can just let the optimization algorithm figure out what they should be. So the idea is, I write down my loss function of how good the recommender is, and then the optimization algorithm just figures out what those numbers should be, what the features of the product should be to best explain the data. For those people who aren't familiar with this idea, it sounds like magic, right? How can the model figure out the features? But the key insight is that these are just parameters in the model like everything else, and so the same optimization algorithm works. The point is, I write down my loss function, and features are discovered automatically that best optimize that loss. So the representations of products and customers follow the same pattern that are used in this model are optimal with respect to the loss. And that's a much nicer position to be in, because instead of trying to figure out how to represent the data, I just have to figure out what good is for my problem. And then the machinery of stochastic gradient descent, the machinery of my optimization algorithm will figure out what to do. Yes? Exactly. So I didn't say the word embedding, but this is exactly an embedding for the Nintendo Switch. So the beauty is, if I change my loss function, I'll get a different representation that will be optimal with respect to that loss. And that's a very powerful idea. So how can I go about using this idea to build a recommender system? The basic method following this principle that almost everybody has heard of is called matrix factorization, right? So I take a big matrix representing all of my behavioral data, where the columns represent the products and the rows represent the customers. And I fill that matrix in with ones and zeros such that the entry is 1 if that customer has bought that product and 0 otherwise. Okay? And this is a pretty big matrix. So it might, in the case of Amazon, it's going to have hundreds of millions of rows. And even if we cap to popular products, it's going to have millions of columns as well. Okay? And then we say, what would happen if we said that this giant matrix was actually the product of 2 smaller matrices? And according to the rules of linear algebra, if you take matrices of the size and shape of the green and blue boxes and multiply them together, you'll get something of the shape of the orange box. And so the idea is, this is an approximation, right? We're saying, how can we best approximate the big orange matrix with the product of 2 smaller matrices? But it's quite a convenient paradigm, because it allows me to represent this big sparse matrix as 2 much smaller and more interpretable ones. And actually, the really nice thing is, so, I was talking about this idea of distributed representations, embeddings, that's features of items that are learned automatically. What I get when I do this is something that I can interpret as representations of my products, embeddings of my products, and representations of my customers as well, right? Every row in the blue matrix is an embedding representation of a customer, and every column in the green matrix is an embedding, a learned representation of a product. So this is the simplest model, the simplest method that follows this principle of learning representations in order to make recommendations. And when I want to make recommendations from this model, I just multiply the 2 small matrices together, and I look for items that have high scores in the result of that multiplication that the customer hasn't already bought. Okay, so that's the idea. And as I say, this is basically the easiest way to get started with distributed representations for recommendations. The reality is, at the scale that I was talking about, this is pretty expensive. So in particular, this constraint that you have a separate vector for every customer leads to models that get very big very quickly. So just an idea, if you had 50 dimensions per customer and 100 million customers, you'd end up with a model that was 20 gigabytes in size just for the raw floating point numbers that represent all those customers. And honestly, models that big are not fun to work with. They're really not fun to optimize as well. And so the trick that we often use to make this scalable is to say, well, the customer representation is just going to be some function of the products that that customer has interacted with, right? So maybe the customer is the average of all of the products that they've bought. And that's much more scalable, because now I'm just learning representations for the products, and the representations of the customers are derived from them. And the other thing that causes scaling challenges with this approach is that if you have lots of products, you can end up with very long training times for this kind of model because it's just a very big matrix. And so an approach that's typically done to make this go faster is we recognize that this matrix is very sparse. It's 0 almost everywhere. And for some particular customer, the 10 millionth 0 is not super informative, so we might subsample the products that the customer didn't buy. Okay, I want to move on and talk about deep learning for recommendations and why I think that might be a good idea. And this is going to connect back to the idea of distributed, automatically discovered representations, but under a much more powerful model. So some of you might have heard of deep learning. You've heard lots of people talking about it this week. It's revolutionized fields in AI like object detection, speech recognition, machine translation. And the point that I want to try and impress upon you or convince you of is that understanding our customers ought to be possible to solve with similar levels of performance. And it's a problem that we at Amazon care very deeply about and is very important to the customer experience. So first I want to motivate why deep learning works and why it might be a good idea to try and understand or represent customers using a neural network. And it's because deep learning has been shown to work really well for problems with complicated unstructured inputs like natural images or sound waves, right? So where you've got very high dimensional data, but every individual element of that data is not very informative on its own, right? So maybe it's individual characters in a string of text or individual pixels in an image. The information content of any one of those things is relatively small, so what you have to do is form representations of that data in order to be able to learn. And this is where deep learning has really excelled, because exactly as I was making the point about with matrix factorization, those representations are learned jointly with the model. I should say that at least a naive application of deep learning has some prerequisites. It tends to need a lot of data if you're going to try and learn complicated representations. It relies on what's now, more than a decade of progress on open source frameworks for doing this kind of work. And also you need access to some GPUs. This won't be the first time this week you've heard this. But given that we've got those things in abundance at Amazon, I think it's a good idea to think about using these kinds of techniques. So what particular aspects of the problem do I think deep learning might be able to speak to? Well, if we think about the matrix factorization approach that I spoke about a couple of slides ago, I think I can probably convince you that it makes some assumptions that are too simple, right? So in particular, it ignores purchase order. Customers who buy the same products in a different order will see the same set of recommendations because it doesn't know what order you buy things in, right? It doesn't know anything about time. Buying things like purchase patterns, customer behavior is very seasonal. Buying things during a sale or before Christmas is very different to regular purchasing. And if you don't factor that into the representations and decisions you make, you're going to come up with suboptimal inferences. Another thing is not all customer interactions have equal importance, but it's quite hard to express that in a general way in the matrix factorization approach. So what I mean by that is, and I'll get to this in more detail in a minute, certain purchases, certain actions are just, everybody does them, they're low information content, right? You buy batteries or an SD card for your digital camera or something like that. That's not telling us very much about you. And so what we want to do is come up with a model that can automatically learn how to deal with all of these complicating factors in order to deliver the best possible recommendations experience that we can. So how do we do it? I've got some examples here that are driven both by a recent movie release and also our celebrity guest at the event. So I should say I'm not a Marvel expert, but it was too topical for me to ignore. So all of my examples are going to relate to movies in the Marvel franchise. But I'll try and explain for those of you that don't have the appropriate cultural reference. So imagine we've got a customer who has purchased or viewed these movies, right? So they've watched Avengers: Infinity War, they've watched Ant-Man and the Wasp, and they've watched Captain Marvel. So Wikipedia tells me that this is the order in which these movies were released, and this is the order that's considered canon for the series, right? So given that you know something about behavioral data like this, can you predict what's coming next? I think you probably can, or at least if you know anything about Marvel, you probably can. And so the techniques that we use to do this are borrowed from similar fields like natural language processing, where predicting conditioned on sequences is just a standard thing to do, right? So if I write the cat sat and ask you what's coming next, you have strong biases about what the next word is likely to be that would be different if I wrote those same words in a different order. So for those of you that are familiar with the technical details, you want to use autoregressive neural networks like convolutional nets or recurrent neural nets that can memorize arbitrary information over an arbitrarily long time period and are sensitive to the order in which events occur. So that's exactly what we do. We use a neural sequence model, a self-attention network, to pay attention to not just what you bought, but also the order in which you bought it. Speaking of self-attention networks, I want to get to this idea that not all customer interactions are of equal importance. So exactly as I was saying a couple of slides ago, some past events you can think of them more like filler, right? The customer, the batteries in their remote control expired and they need to buy new ones, or they bought an SD card or a USB cable or something. Doesn't tell us very much about the customer. We don't want to drive more recommendations of batteries based on your purchases of batteries, because that's not a very pleasant customer experience. Whereas other things that a customer does reveal deep, long-lasting preferences or traits or things that are going to be much more durable over time. So if I look at your sequence of purchases, I might be able to figure out who your favorite authors are or which film directors you like. The series of books that you're reading at the moment. I might be able to tell that you have a pet cat or a dog, or you have small children. I can infer that based on the implicit information in past actions that you've taken, and that's going to be important to contextualize future recommendations that I want to make. So you've got this situation where past events are not of equal importance, but I don't really want to use heuristics to say which things are important and which aren't, because I'm going to do a bad job of figuring it out. What I'd ideally like to do is learn which events are more predictive of future actions than which aren't. And so we do that using an idea called attention, which again was borrowed from these neural sequence models, I think first applied to machine translation, but it's now been applied all over the place. So the idea here is I've used colors to code the relative importance of these different past events, and I've snuck in the fact that the person watched the news a few months ago or something like that. So in order to predict what the customer is going to watch next, I probably want to ignore the fact that they watched the news, because there's much stronger information coming from the other events. And so the idea is I ask my model, my neural network, to, along with representing each individual event that the customer has done, to come up with some idea of the importance of that event for predicting what's going to happen in the future, right? And this is what's called an attention score. And in these neural attention models, the thing that's really killer is that these attention scores are learned jointly along with the model, right? So the model just figures out which things are important and which aren't in order to predict the future. And this is the idea that we're using in order to form these representations of customers and make recommendations to them. And the last thing I want to speak about briefly is how we deal with time. So in order to motivate that time might be important here, imagine that this customer had watched the items in this at these particular times, right? So for those of you that don't know, these dates are when these movies were released. So what we know is that this customer is watching the movies as soon as they're released, okay? That probably makes us feel stronger that the customer is even more likely to watch this movie because they're watching the films as soon as they become available. An even stronger signal might be they watched all 3 of the past movies yesterday, right? So, you know, they've just been on some 48-hour Marvel binge, and that's going to make us feel even more strongly that what they want is the next movie in the Marvel series. But the thing that's interesting here is you have to contextualize this against the time at which you're making the prediction as well. So in this case, this is March 2019, and the Avengers Endgame, at least in the UK, was released in May, right? So the other thing that's important here is if the customer watched these things in March, that tells me something different to if they watched them just before the release date of the new film. Right? And that's especially important when I contextualize when I'm making the prediction. So if I know it's March, then Avengers Endgame shouldn't be possible because it's not been released yet. Right? So the predictions that I make need to contextualize when the user did the past actions, but also the point in time at which we're making the prediction, at which we're making the recommendations. And so I really want those time series effects in the model. This is a sort of slightly contrived example, but you can imagine it being that much more important when it comes to explaining seasonal behavior like holiday purchases or sale behavior, that kind of stuff. And you can apply this same idea to other kind of short-term contextual signals, like if you ask the model, oh, I'm interested in recommendations in the category of ebooks, then Avengers Endgame doesn't look like a very good idea here. Maybe you've got information, for instance, that the user is currently browsing in the category of ebooks, right? So you want to not recommend the new Avengers film to them because they're interested in ebooks, but you do want to use context from the films that they've watched in order to maybe find books that are relevant, that exist in that universe, that kind of thing. And so the way that we do that is, in addition to every event, every product that the customer has interacted with in the past, we also tell our neural network the point in time at which those events occurred and how long ago they were relative to the point of prediction. And because this is a very complicated problem and existing time series models don't deal very well with data of this form, what we do is we just allow the neural network to learn how to mix the representations of time with the representations of products in order to come up with the best possible representation for predicting the future. And to deal with the fact that customer behavior changes very rapidly, like aggregated customer behavior, what's popular, we also retrain the model very frequently. So it's important to be responsive to quick changing events. So I hope what I've tried to do is give you some ideas of why I think deep learning is appropriate for the recommendations problem. And it's because customer behavior is at least as rich as natural images or sound waves, right? There's just as much complexity in that behavior. And instead of trying to extract it manually, we want to use models that can figure out how to represent it automatically. And I think the idea is that deep learning, the discipline of neural networks, provides a coherent framework for doing that, because it allows us to deal with these rich unstructured inputs and learn representations that are optimal with respect to the loss function, the problem that we're asking the model to solve. And the thing that's really important, particularly when I try and contextualize the next few slides, is that all of this behavior is driven by the loss function, right? So I say what good is, and the model figures out how everything else should be represented in order to optimize that loss. And so now I'm going to get onto the last part of the talk. This part is the most technical and the hardest for me to explain in a non-technical way. So I'm going to do my best, but apologies if I screw it up. Yes?
You said that you will have to retrain often.
Yeah.
I mean, it's not going to get rid of the effect that you probably have to filter the recommendations on the output end as well, because probably people might want to, remove items that are no longer for sale, for example.
Yes.
You probably won't retrain that often, but also the fact that somebody bought something, you don't want that to be still in the recommender carousel. So it's not a silver bullet this, but it's closer.
No, you're right. I mean, there are certain problems that it's not worth trying to solve with machine learning, like it's a bad idea to recommend people things that they just bought. We can use filtering instead to solve that. And that's exactly what we do. So we retrain, every day, and we make predictions with the best state of knowledge that we have at the point that we make recommendations, but you're absolutely right. Like we don't want to damage the customer experience or erode trust by making just obviously stupid recommendations like the thing that you just bought 5 minutes ago. And so we'll use filtering to fix that. Okay, so I'm going to try and motivate a different way of thinking about the recommendations problem. And as I said, this stuff is a little bit technical, so if I make a mess of it, I'm sorry. But I'll do my best. So what I want to do is I want to motivate the paradigm that we use, the mental paradigm that we use when we think about the recommendations problem, right? So most of the success of machine learning, and indeed almost all of the recommendations literature, phrases recommendations as a prediction problem, as what we would call a supervised learning problem, right? Where you know the right answer, or you know the behavior that you're trying to predict, and you ask the model to recover that behavior. Some of you will be familiar with a paradigm that's received a lot more attention recently that's behind the successes of things like AlphaGo or the computers playing arcade games, that kind of stuff. This is the rise of, and also I think we've heard something about it in the field of robotics. This is the rise of machine learning for optimizing decision problems, reinforcement learning, or its sort of slightly impoverished, stateless cousin, bandit learning. And what I'm going to try and convince you of is that that's the framework that we should be using to think about recommendations. So I've sort of implicitly said along the course of this talk that when we build recommendations, what we're trying to do is solve prediction problems. Right? What we're trying to do is predict what the customer is going to do next, given what they've done in the past. And as I said, the literature basically assumes that this is the right thing to do. You can interpret the loss functions that are being used as being loss functions that optimize for prediction problems. But I want you to think of a thought experiment, right? Imagine that we solved that problem perfectly. Imagine that we could perfectly predict what our customers were going to do next. By definition, the output of that model would make for terrible recommendations against the backdrop of what we're trying to achieve with a recommender system, which is driving this serendipitous discovery, right? So instead, what we want to do is build a recommender system that optimizes for what we consider to be positive outcomes, okay? And those positive outcomes speak to this idea of serendipity, but it can be more flexible than that. It can be whatever we think is a good outcome with respect to the recommendations problem. So a simple example would be you want to maximize the click rate on the recommendations that you serve. One that I think speaks more broadly to the kind of outcomes that we're interested in is you want to maximize long-term customer engagement with your store, okay? And the idea is that we want to use notions from reinforcement learning to optimize this directly. So what we want to do is ask the question of, what do I want to recommend to the customer? What can I observe about what happens when I make those recommendations? And can I make inferences about what would have happened if I'd served different recommendations instead? And can I use those inferences to directly optimize this long-term engagement that customers have with the store? So when we're solving prediction problems, what we do is we write down a model that maps from raw inputs to, in the case of recommendations, a high-dimensional categorical output, right? It's all possible products in the Amazon store. And when we're training that model, what we do is we set the weights to some values, ask the model what it thinks about some particular training example, compare that to the right answer, and adjust the model's parameters so that the model's output gets a bit closer to the right answer. And what's important here is that we know what the right answer is, right? We know the thing that we're trying to predict. In contrast, for a decision problem, recommendations, if you want to maximize engagement that your customers have with recommendations, you're making decisions, and the data that you collect only relates to the decisions, the actions that you chose to take, right? So I can build a model of what happens when I make the decision, but I don't know what would have happened if I'd done something different. I know that conditioned on the fact that I showed you the next Marvel movie, there was this probability that you clicked on it or not, but I can't say what would have happened if I decided to show you a Batman movie instead, or a cuddly toy or something like that. And that's exactly the question that I want to ask if I'm looking to maximize long-term engagement. And so my attempt to explain the trick that we use to make this work is that we add some randomness into the decisions that we make, right? So instead of deterministically showing you the best products all of the time, if sometimes we show you something that we think you might like, but we're not sure, and we do that with randomness, then we can compare the conditions that are similar to one another and look at the outcomes that emerged from them, right? So I can aggregate across all of the instances where I had customers with certain sets of interests that I showed certain sets of things to, and I can say, well, on aggregate, what looks like the better thing to have done? That's a very non-technical description of it, but what we're really doing under the hood is we're using ideas from counterfactual learning, we're using importance sampling estimates to figure out what would have happened if we'd done something different. So the practical implementation of this, and this is why I said I think it's quite hard to build kind of commodity systems that behave in this way, is that we keep a log of what we recommended, to whom, and what happened, and also the randomness that we injected at the point that we made the recommendation. And using these ideas from counterfactual learning, we can turn that log of what we did and the probability with which we did it into a loss function that more directly reflects the decision problem that we're asking the model to solve. And when you build a system like this, you have the property that over time, you've added a feedback loop to the system, right? And over time, it's going to get better and better and better, because it's going to stop doing the things that don't work, and it will double down, it will do more of the things that look like they're working. And so that's exactly what we do. It works pretty well, but there are some issues with it, and I want to briefly touch on what those are. So the first thing is when you're working from log data with respect to recommendations impressions, you have to deal with the fact that the data is pretty noisy. So most recommendations don't work, right? Most customers do not come to Amazon to see their recommendations, and if you guess with millions of possible options, you'll be wrong a lot of the time anyway, right? So almost all of the data is user didn't click, user didn't buy the thing. And even in the cases where the outcome is not zero, where the user did respond, you've got outcomes that are very unequal in terms of the value, right? So not everything that you can buy or interact with has equal value with respect to long-term engagement, right? If I convince you that it would be a good idea to sign up for Prime or join the Kindle lending library or something like that, that's an outcome with tremendous long-term value versus selling you a pack of batteries or something like that. So you've got this very long tail of the distribution of values, even conditioned on the fact that the user actually interacts with the recommendation at all. And that makes for a challenging learning problem that you have to be quite careful about how you approach. And the other thing is, these kinds of problems, the ones where you're learning from partial feedback, where you're learning from log data, are subject to what's called an explore-exploit dilemma. Okay, so I said the trick to get around the problem of not knowing what would have happened if you'd done something different is, with some probability, do something different. But what that probability should be is a difficult thing to tune, and this is the thing that regulates what we call the explore-exploit dilemma, right? So if I set the probability to 1 of doing something that I think is suboptimal, I'm going to upset customers by showing irrelevant recommendations all the time. If I set it to 0, I have no data from which to learn what would have happened if I'd done something different. And exactly how to tune that balance is a tricky problem. So I'm going to wrap up now. I have a couple of minutes left. And what I want to do is just reiterate these ideas that I've tried to convince you of about how we can think about the recommendations problem in a slightly different way. So the first thing that I tried to convince you of is this powerful idea of implicit featurization, distributed representations, because it turns feature engineering into learning, right? It turns trying to figure out by hand what the right representation is to allowing the machine and the loss function to drive the optimal representation with respect to the task. And that's a very powerful idea. I've also tried to convince you that tools from deep learning should be applied to the recommendations problem, because if you phrase the problem correctly, then neural nets can do a good job of understanding customers and their preferences and traits in the same way that they can images and sound waves. And the last thing that I tried to convince you of was how we think of recommendations, or how we should think of recommendations as more of a decision problem than a prediction problem. And that's it. Thank you.